When describing a frequency distribution, if we only describe the location or the center of the distribution, we are going to miss some very important information contained in the sample that we have. That's specifically going to be information regarding how much variability there was in the sample. If the data are very different from one another, then we're going to have high variability. If the data are all very much alike, then we might have low variability. Now, this is not captured by simply reporting the location or the center, and as a result, we need to have ways of measuring the sample variability or the variability of a frequency distribution. So if we describe only the location of the frequency distribution, that's going to overlook the amount of variability in a data set. We might also refer to this as the amount of spread or the amount of dispersion in a data set. The sample measures of variability are going to capture how much spread there is in the observed data. So what measures of variability do we have? Well, to describe how much spread actually exists, then we'll turn to, broadly speaking, measures of variability. And overall, each of these is going to measure the diversity of values that's actually observed, or the total spread. How different are the values from one another? And they measure these in slightly different ways. So the sample range is going to be a measure of the difference between the largest and the smallest observation in the sample. It's going to tell us over what full range were the data actually observed, what is the difference between the smallest possible value and the largest possible value. The sample interquartile range, or the sample IQR, is going to be the difference between the 75th sample percentile and the 25th sample percentile. And so this is going to be very similar to the sample range in that it's measuring the sort of full spread, except instead of us looking at all of the data, we throw away the bottom 25% and we throw away the top 25%. And we say, of the data that are remaining, how much spread was there in it? What was the total range? And what this is going to do is this is going to say that if you have one or two really large extreme values that are not representative of most of the trends in the data, the interquartile range is not going to be impacted by this. And so it generalizes the range, but it becomes a little bit more robust than the range as well. We'll often write this as Q3 minus Q1, so that is the third quartile minus the first quartile, hence the interquartile range. The sample variance is approximately, although when we see the formula in just a moment, we'll see why it's only approximately, the average squared distance from the observations to the sample mean. So if you take how far, on average, were our data points to the sample mean of those data points, that's going to give you the variance. But we say it's only approximately because if you actually look at the formula here, so when we're talking about our sample variance, we use the notation S squared, and the formula for the sample variance is going to be given by this. And so you can see in the summation, right, we have the sum over all of our observations, xi minus x bar squared. So that's going to give us the overall total difference between each data point and its mean squared, and we add those all up. But then instead of dividing by n, we divide by n minus 1. And the rationale for this will be discussed if you think about the properties of these estimators. But overall, when we're typically thinking about the sample variance, we think about dividing by n minus 1. So it's not exactly the average, it's only approximately the average. But if you imagine n being a very large number, right, you take n to be 1,000,000, for instance, dividing by 1,000,000 or dividing by 999,999 are essentially the same thing. Okay, so we can think about the sample variance as being the average squared distance from each data point to the sample mean. But we just have to remember, if we're actually calculating it, we don't use the average, we don't divide by n, we divide by n minus 1. The sample standard deviation can also be discussed. The sample standard deviation is the square root of the sample variance. We use S to denote this. So S squared for the variance, S for the sample standard deviation. And we can go back and forth from one to the other. Take a look at some examples here then. We have the following 10 observations, and we want to know, well, what is the sample range? And so if we look at the observations, the smallest value is a 1, the largest value is a 5, and so the sample range is going to be 5 minus 1, which is 4. Okay, now what about the sample IQR? So the sample IQR is going to require us to have the 25th and the 75th percentile. Okay, and so if we want to find, well, what is the 25th percentile, then what we need to do is we need to take p times n, and so p in this case would be 0.25 times by n, which is 10, right? And so that's going to give us 2.5. And so then what we know is that we need to take the third smallest observation, so that's x3. If we then instead look at the 75th percentile, we do the same thing except with p being 0.75. That's going to give us 7.5, and so then we need to take x8. Right? And so we need the third smallest and the 8th smallest value. Now there are 4 ones, right? 1, 2, 3, and 4. And so the third smallest value is going to be a 1 here. And then if we count through remaining, right, then we have our next 2 for 5 and 6 are 2s. And so then 7 and 8 are both 3s. And so that's going to be a 3. And so then we take 3 minus 1 gives us 2 for the interquartile range. So the sample interquartile range here is going to be 2. So we order the data. We look for the 25th percentile, which requires the third point. That's a 3, or that's a 1 rather. We look at the 75th percentile, which requires the 8th point. That is a 3. The difference between those two gives us the IQR, which is 2. Continuing here, what is the sample variance? And so if we want the sample variance here, right, then what we're going to need to do is we're going to first need to find what is the sample mean, right? And the sample mean is going to be given to us by the summation over all of our values here, dividing that by 10. So that's 1 over 10, 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 3 plus 5 plus 5. And so that's going to give us 2.4 if we work out what that is. And then what we need to do is we need to take s squared, right? And s squared is going to be 1 divided by n minus 1, so that's 10 minus 1. And then we want to sum over all of our values, but we want to take the individual values minus the mean squared. And so, for instance, you'd have 1 minus 2.4 squared, right? But we're going to have that actually another 3 times here, right? So what I can just do is I can say plus another 3 of 1 minus 2.4 is negative 1.4 squared. Okay. And then we have 2 of them that are the value of 2. So that'll be 2 times 2 minus 2.4 squared. Plus there's another 2 of them at 3. So that's 3 minus 2.4 squared. Plus another 2 of them at 5. Right? So that's 5 minus 2.4 squared. Okay, and so it's a little bit tedious to work through, but if we simplify down a little bit, right, we can sort of group up the terms with our multiplication here rather than writing them all out. And if we work out this, that'll give us our sample variance, right? So plugging that into a computer or into a calculator will work out what value we're looking for there. So we get our 2.4 as our mean, and then we can calculate out our sample variance here, right? And so here we've explicitly written each of them out, but we've done that subtraction. So that's 1 minus 2.4, 1 minus 2.4, 1 minus 2.4, and so forth, right? Through all of the different values here, you work out what that is. That gives us 22.4 divided by 9. Again, remember, we divide by n minus 1, not n. And so that's a 2.48. Repeating. Finally, if we want the sample standard deviation, the sample standard deviation is the square root of the sample variance. And so that's the square root of that 2.48 we just calculated, right, which gives us 1.578. Okay. Look at another example here. We have 15 adults who have their systolic blood pressure measured. The results are shown, and we want the sample range. And so then going through, what we need to do is we need to work out, well, what is the smallest possible value? I believe that smallest value here is going to be a 98.13, right? I don't believe any of the other values are even below 100. And then we have to go through and we have to find what is the largest value. And I think the largest value, just looking at it quick here, is probably, oh, there's a 137 over here. So it's probably that 137 actually, right? So then what we would have is this 137.27 minus this 98.13. Okay, and that's going to give us the full range of the data. So our minimum 98.13, our maximum is 137.27. So you take the difference between those two, and that gives us a range of 39.14. So all of the observations in the sample fell over a range of 39.14 units. Another example here, we have a random sample of 5 male and 5 female emperor penguins. Their heights are measured and given to us there. And we want the IQR for the male penguin heights. And so if we have n equals 5, right, then we need the 25th and the 75th percentile. So we're going to need 0.25 rather, times by 5, and we're going to need 0.75 times by 5. Okay, and so then this is ultimately going to give us, what, 5 over 4, and this is going to give us, which is, sorry, 1.25 there, okay, and then this one is going to give us 15 over 4, 3 times that, right? And so that is, what, 3.75, I think. Okay. And so in this case, what this tells us is that we need to round up, right? So we need the second point, and in this case, we round up, and we need the fourth point. And so we're always going to be taking x of 4 minus x of 2. Okay, so the second highest and the second lowest points. And so then we can go through our data here, and we can see that, right? So for the male penguins, our smallest is 119, and then we have a 121, and then we have a 1, so 121 is x of 2. Okay, and then we have our 123, 124, and so then the 124 is x of 4. Okay, and so working through that, we are going to end up with 124 minus 121, which gives us 3 as our IQR here. Okay, and so if we erase this, we can take a look at that calculation again, step by step here, right? So n equals 5, we require the 25th percentile is 1.25, right? N times p, and so that requires x2. The 75th percentile requires x4, which is 124. So then the difference is 124 minus 121, or 3. Now, what about the IQR for the female penguins? Well, we're going to need to do the same thing, right? There are 5 of them here as well. And so we're still going to need the second and the fourth point. And so 115, 117, 117 is point number 2, 118, and then 120, 120 is point number 4. And so then we'll find that the IQR here is also 3. Okay, so 117 and 120, so the IQR is going to be 3 here. And what about the IQR for all of the penguin heights? Well, in this case, right, we have n equals 10 now, instead of n equaling 5, right? So with n equals 10, then the 25th percentile is going to correspond to n times p being 10 times 0.25. So that's 2.5, right? So that's going to be point number 3. And then for the 75th percentile, we're going to have n times p is given to us by 10 times 0.75, right? And so that is 7.5. And so then we need the 8th and the 3rd point. Okay, and so then if we go through, again, all of our points in order here, we're going to start with the smallest being 115, and then 117 and 118 is number 3. Okay, and then if we look at what are the highest points, right, and we can count backwards, the 10th highest is going to be this 128, right, and then the 124 comes next, and then after the 124, it looks like we would have a 123. Okay, and so then we'll have 123 minus 118, and that will give us the range there, okay, the interquartile range of all of them. So again, stepping through that, n equals 10, our 25th percentile corresponds to x3. Our 75th percentile corresponds to x8, and so that is 120. I believe that should actually be 123 based on the data that are recorded here. And so then we difference those and find an IQR of 5. Let's look at one last example here. We have students in a university that are taking introductory math classes. There are a total of 209 students in these classes, and there are 4 probability sections, and so those are going to have 80, 52, 45, and 32 students respectively. They're also going to have 2 sections of statistics with 119 and 90 students respectively. We want the sample variance in class sizes for the probability sections. And so here, right, we need first what is x bar. And to get x bar, you could add up all of those numbers and divide by 4, but we know that the addition of all of those numbers gives us the 209 students in all of them. So the x bar here is going to be 209 divided by 4. And then what we would want for s squared here, right, is going to be 1 divided by n minus 1. So n in this case is going to be 4, so 4 minus 1. And then we would take each of our observations, so that'll be 80 minus x bar squared plus 52 minus x bar squared plus 45 minus x bar squared plus the last one, 32 minus x bar squared. Right? And that's going to give us our sample variance in this case. Right? And so then working through again, you'll want to plug in to a calculator here. So x bar is going to be 52.25. S squared, 1 divided by 4 minus 1, right? So that gives us 1 over n minus 1, and then we add through the different points here, and that's going to give us 410.92 approximately. For part B, what is the sample standard deviation in class sizes for our statistics sections? Okay, so here, right, if we have x bar, that's going to simply be 209 divided by 2, right? And so that should be 104.5, I believe. And so then if you want the sample variance, right, and to get the sample standard deviation, first we calculate the sample variance. That's going to be 1 divided by 2 minus 1, right? So we're going to end up just having this constant out front be 1, and so we can ignore that. But in this case, then we would take the 119 minus 104.5 squared plus 90 minus 104.5 squared, okay? And so then we'd work out, well, what is all of that? And then that would give us our answer here, right? So that's going to be our S squared. To get the sample standard deviation, you take the square root of that value, okay? And so then working out what that actually works out to, right? We have 104.5 as the mean. So then S squared is going to be equal to 420.5, right? Where again, we're dividing by 2 minus 1, and so we don't need to write that out. And so then the square root of that gives us 20.51 approximately. Okay. What are the units associated with the answers in A and B? And so if we think about what we're doing with our sample variance, right, we're squaring everything. And so our sample mean would be in the units measured in students. There's a certain average. There's 104.5 students per class on average, right? But the variance squares that. And so the units are going to be students squared in our variance. However, in the standard deviation, we then take the square root, and so we're back to having students again. So with our variance, it's going to be the units squared, so in this case, students squared, and in the standard deviation, it's just going to be the students. So variance will have students squared. This is not going to be easy to interpret, right? What does it mean to have, 400 squared students as the variability? It's not always clear. In part B, standard deviation is going to be recorded in the students. This is going to give us an easier to interpret value. So we could say something like there are 104.5 students on average. The standard deviation is 20.51 students. And so that's going to give us at least some sense of how much variability on the same scale are we thinking about. Now, suppose that all 209 students are in the same calculus section. What is the variance of the class size for calculus? Okay, and so here, right, the important thing for us to note is that we just have n equals 1. And so to calculate our variance, right, S squared, we would have to go 1 divided by n minus 1. And immediately we're going to bump into a problem, right? Because this is going to be 1 over 0, which is not defined, right? This is indeterminate. And so as a result, we do not have a variance in this case. If you only have one data point, you do not have an estimated sample variance, okay? And so it's undefined. Anytime you only have n equals 1, you're going to have an undefined variance. Importantly, this is because we can't divide by 0. It's also important to note that this is not the same as saying that there is 0 variability in data. If you're going to have 0 variability in data, what you would observe is every observation happens to be the same, right? So if you had, say, 100 total students and every section was 25 students large, there'd be no variability in the section sizes. But if you only have one observation, then you don't have variance defined. You're not going to say that the variance is 0. You're going to say that it's undefined. So if we want to completely describe the behavior of a frequency distribution, then we have to capture the variability in addition to the location. This is going to require measures of sample variability, whether that's the range, interquartile range, variance, or standard deviation, or some combination of them. All of them are going to give slightly different interpretations of what we mean by the spread or by the dispersion. All of them are going to be useful in certain circumstances. And when we provide them, we're giving a lot of information about how are the data actually distributed, how are they dispersed, how much spread are there, which is important information for us to be making informed decisions about the data that we've actually observed.